There is an ocean beneath Antarctica that nobody has fully explored. A frozen world hiding liquid water, ancient life, and secrets that could change everything we know about our planet. Scientists who study it admit they are terrified of what they might find next. Some discoveries down there challenge what we thought was possible. If you want to understand why this hidden ocean matters, stay with us. And if you enjoy deep dives into Earth's mysteries, subscribe for more. The Southern Ocean surrounds Antarctica like a fortress. It is the most violent ring of water on the planet. Waves here can reach heights of 70 feet during winter storms. The wind screams across the water at speeds that would flip most ships. No land breaks the current as it circles the bottom of the world. This means the ocean spins endlessly, building momentum, gathering fury. Sailors who venture here call it the most dangerous water they have ever crossed. The temperature barely climbs above freezing even in summer. Ice forms on ship decks within minutes. Equipment fails. Ropes freeze solid. Every expedition south is a gamble with nature. But the real mystery is not what sits on top. It is what hides below. Beneath the waves lies something stranger than the storms above. The Southern Ocean acts as a barrier, isolating Antarctica from the rest of the world. Warm currents from the north never make it through. Cold water sinks and spreads along the ocean floor, feeding into every ocean on Earth. Scientists estimate that more than half of the deep ocean water across the globe originates here. This cold pulse affects weather patterns, marine life, and climate systems thousands of miles away. Yet we know almost nothing about what lives in these depths. Research vessels can only operate a few months each year. The ice closes in like a trap when winter arrives. Submarines that work elsewhere struggle with the cold. Instruments crack, cameras fog. Even satellites have trouble seeing through the constant cloud cover. The Southern Ocean is a blind spot on our maps. And what makes it truly unsettling is this. Beneath the ice shelves that fringe Antarctica, the ocean continues. It does not stop at the coastline. It flows under ice thicker than skyscrapers are tall. It carves channels and caverns in the dark. There are bays the size of entire states hidden under solid ice. Scientists have only just begun to send probes into these regions. What they are finding does not match any predictions. The models were wrong. The assumptions were incomplete. Every new expedition reveals something that forces researchers to rewrite their theories. Marine biologists have pulled up creatures from these waters that look like they belong on another planet. Transparent fish with antifreeze proteins in their blood. Animals that have evolved in isolation for millions of years. And the deeper the robots go, the stranger it gets. This ocean is not empty. It is teeming, thriving, adapting. And it holds clues to how life can survive in the most extreme conditions imaginable. If life can exist here beneath miles of ice, in water colder than your freezer, then maybe it can exist elsewhere in the universe. Maybe the frozen moons of Jupiter and Saturn hide oceans just like this one. Maybe we are looking at a blueprint for life beyond Earth. That is why scientists keep going back. Despite the danger, despite the cost, despite the fear, Antarctica is covered by ice shelves that float on the ocean like massive platforms. These shelves are not small. The Ross Ice Shelf alone is roughly the size of France. The Rhone Ice Shelf rivals the state of California. Together they cover an area larger than the entire country of Mexico. But here is what most people miss. These shelves are floating. They rest on water, not land. Beneath them lies a dark ocean that has been hidden from sunlight for thousands of years. The ice above is thick. In some places it measures over 3,000 feet from top to bottom. Imagine stacking 10 Eiffel Towers on top of each other. That is how much ice separates the ocean below from the sky above. And this ice does not sit still. It flows like a river in slow motion, creeping toward the sea at a rate of several feet per day. As it moves, it grinds and cracks and reshapes the water beneath. Scientists did not understand what was happening under these shelves until recently. For decades, they assumed the ocean below was calm, cold, and mostly lifeless. They were wrong on all counts. When researchers finally sent cameras and sensors through boreholes drilled in the ice, they discovered currents, strong ones, water rushing through channels carved into the bottom of the ice, tides pushing and pulling with surprising force. The ocean here is active. It melts the ice from below, carving enormous cavities that can swallow entire cities. In some regions, warm water seeps in from the deep ocean and eats away at the ice like acid. This process is invisible from above. Satellites see nothing. Even ground teams drilling on the shelf have no idea what is happening hundreds of feet below their boots. The ice looks solid, stable, permanent. Underneath, it is dissolving, and the speed of this melting is accelerating. Temperature readings taken over the past 20 years show the water is getting warmer. Not by much, just a fraction of a degree. But in an environment this cold, even tiny changes have massive effects. The ice shelves act like corks in a bottle. They hold back glaciers on land, preventing them from sliding into the sea. If the shelves weaken or break apart, those glaciers will accelerate. They will dump ice into the ocean at rates never seen in human history. Sea levels will rise, coastlines will change, cities will flood. This is not speculation, it is physics, and it is already happening in some parts of Antarctica. The Larsen ice shelf on the Antarctic peninsula has collapsed in stages over the past 3 decades. First, small sections broke away, then larger pieces. In 2002, an area the size of Rhode Island shattered into thousands of icebergs in just over a month. Scientists watched in real time as the shelf disintegrated. What terrifies them now is that other shelves show the same warning signs. Cracks forming, melt rates increasing, structural weakness spreading like fractures in glass. Beneath the Antarctic ice sheet, buried under more than 2 miles of solid ice, lies Lake Vostok. It is one of the largest freshwater lakes on Earth. The lake stretches for roughly 160 miles in length and 30 miles across at its widest point. The water sits in complete darkness, sealed off from the atmosphere for an estimated 15 million years. No sunlight has touched its water since before humans existed. No wind has rippled its depths. It is a time capsule, frozen in place by the weight of ice pressing down from above. Russian scientists discovered Lake Vostok in the 1970s using ice-penetrating radar. At first, they did not believe the readings. How could liquid water exist so deep beneath the ice? The pressure alone should have frozen it solid. But the weight of the ice creates friction, and friction generates heat, just enough to keep the water at the bottom from freezing. The temperature of the lake hovers around -3 degrees Celsius. That is below the normal freezing point of water, yet the lake remains liquid because of the immense pressure. It is like a natural antifreeze experiment on a planetary scale. For decades, scientists debated whether to drill into Lake Vostok. The ethical questions were staggering. If life existed in the lake, drilling could contaminate it with surface bacteria. If the lake held ancient microbes unknown to science, bringing them to the surface could be dangerous. But the temptation was too strong. In 2012, Russian researchers finally broke through the ice and reached the water below. They used thermal drills to melt a narrow shaft, carefully avoiding chemical contamination. When they pulled up samples, they found something astonishing. The water was not sterile. It contained DNA, genetic material from thousands of different species, bacteria that could survive in extreme cold, microbes that had adapted to crushing pressure and zero light. Some of the genetic sequences did not match anything in existing databases. They were completely unknown to science. This raised a chilling question. What else is living down there? The samples came from the very top layer of the lake. The deepest parts, over 3,000 feet below the ice, remain unexplored. No camera has ever seen the lake floor. No instrument has measured what swims in those depths. Scientists theorize that the lake could harbor entire ecosystems built on chemosynthesis rather than photosynthesis. Instead of relying on sunlight, life could draw energy from chemicals in the rocks below. Volcanic vents might heat pockets of water, creating habitats for complex organisms. It sounds like science fiction, yet we have found similar ecosystems in Earth's oceans, thriving around hydrothermal vents miles below the waves. If it can happen in the deep ocean, why not in a subglacial lake? Some researchers believe Lake Vostok is a model for what might exist on Europa, one of Jupiter's moons. Europa is covered in ice, with a liquid ocean beneath. If life evolved in Lake Vostok, isolated and extreme, then life could evolve on Europa under similar conditions. This makes Lake Vostok one of the most important research sites in astrobiology, but it also makes it dangerous. Drilling deeper risks disturbing an environment that has remained undisturbed for millions of years. When scientists finally started drilling into subglacial lakes beneath Antarctica, they expected to find sterile water or maybe a few hardy bacteria. What they pulled up was far stranger. The first samples came from Lake Whillans, a smaller lake buried under half a mile of ice in West Antarctica. In 2013, a team of researchers used a high-pressure hot water drill to bore through the ice without contaminating the lake below. They sterilized every piece of equipment. They filtered the drilling water. They worked in conditions colder than most freezers. When the drill finally punched through into the lake, they lowered instruments and collection bottles into the black water. What came back up shocked everyone. The water was teeming with life, nearly 4,000 different species of bacteria and archaea. Single-celled organisms thriving in water that never sees sunlight, never exchanges gases with the atmosphere, and sits at temperatures just above freezing. These microbes were not dormant. They were actively metabolizing, reproducing, and feeding. But feeding on what? There is no sunlight for photosynthesis, no plants, no algae. The answer lies in the chemistry of the water and the rocks below. The microbes survive by breaking down minerals and organic material trapped in the ice and sediment. Some feed on methane, others consume sulfur compounds. A few derive energy from iron in the bedrock. It is a completely independent ecosystem, cut off from the rest of the planet, running on chemistry alone. Scientists call it a chemosynthetic ecosystem, and it mirrors what we find near deep-sea hydrothermal vents. The difference is, these organisms have been isolated for tens of thousands of years, possibly longer. Evolution has taken a different path here. When researchers sequenced the DNA from Lake Whillans, they found genetic lineages that diverged from surface relatives ages ago. These are not recent arrivals, they are ancient survivors, but the truly unsettling discovery came when they analyzed the water chemistry. The lake is not stagnant. It is connected to other lakes beneath the ice through a network of channels and rivers. Water flows from one lake to another, carrying nutrients and possibly life. This means the subglacial lakes of Antarctica are not isolated pockets. They form a hidden network, a vast underground ocean system stretching across the continent. Scientists estimate there are more than 400 known lakes beneath the ice, and probably many more waiting to be discovered. Some are small, just a few miles across. Others rival the Great Lakes in size, and they are all linked, at least partially, by water flow. What lives in the deeper, larger lakes remains unknown. Lake Vostok, Lake Ellsworth, and dozens of others have barely been sampled. The drilling projects are expensive, risky, and controversial. Environmental groups worry about contamination. Governments debate funding. Scientists argue over methods. Meanwhile, the lakes sit in darkness, holding secrets that could redefine our understanding of life. One of the most disturbing findings is this. Some of the microbes pulled from these lakes show resistance to extreme conditions that do not exist in their environment. They can survive radiation levels far higher than anything found beneath the ice. They tolerate temperature swings that never occur in the stable cold of the lake. Why would they evolve these defenses? One theory is that these organisms originated elsewhere. Maybe they were carried deep into the ice by ancient water flows. Maybe they fell from the atmosphere millions of years ago when Antarctica had a different climate. Or maybe they have been here so long that they carry genetic traits from an earlier era when the continent was not frozen. In 2015, scientists exploring the underside of an Antarctic ice shelf made a discovery that should not have been possible. They were drilling through the Ross ice shelf, aiming to study the ocean currents below. The drill site was more than 500 miles from open water. The ice above was over 1,000 feet thick. No sunlight reached this place. The water was colder than most life on Earth can tolerate. When the camera dropped into the water, the researchers expected to see nothing. Maybe some bacteria. Maybe dead sediment drifting in the current. Instead, they saw animals. Small, translucent creatures swimming past the lens. Amphipods, a type of crustacean moving with purpose through the frozen water. Then a fish glided by. Then another. These were not corpses drifting in from the open ocean. They were alive, thriving, hunting. The researchers were stunned. How could complex animals survive in total darkness, under miles of ice, with no obvious food source? The answer is still not fully understood. The leading theory is that these creatures feed on microbes and organic material carried by ocean currents from the open sea. The water beneath the ice shelves is not stagnant. It flows. Tides push it in and out. Currents circulate nutrients, and wherever there is food, life finds a way. But the distances involved are staggering. Some of these creatures live hundreds of miles from the nearest source of sunlight-derived food. They have adapted to survive on scraps, on the faintest trickle of energy filtering in from the outside world. Their metabolism is slow, they move carefully, conserving energy. They reproduce rarely, but they endure. What makes this discovery truly unsettling is how long these animals have been living there. The ice shelves have been in place for thousands of years. That means these populations have been isolated for millennia, cut off from their relatives in the open ocean. Evolution has had time to work on them. Some show physical differences from their surface cousins. Larger eyes in some cases, different body shapes in others. They are diverging, slowly becoming something new, and they are not alone. Subsequent dives and camera drops have found entire communities under the ice. Small fish, jellyfish, worms burrowing into the ice itself, crustaceans scavenging along the underside of the shelf. Each discovery raises more questions. How do they navigate in the dark? How do they find mates? How do they avoid predators when there is nowhere to hide? Scientists have only scratched the surface of this hidden ecosystem. The technology to explore beneath ice shelves is still primitive. Most camera drops last only a few hours. Battery life is limited. The cold drains power fast. Retrieving equipment is difficult and dangerous. Yet every expedition finds something new, something unexpected, and the implications go far beyond Antarctica. If life can thrive in these conditions, beneath ice, in darkness, in water barely above freezing, then the same could be true on other worlds. The moons of Jupiter and Saturn are covered in ice. Beneath that ice, scientists believe there are oceans, liquid water kept warm by tidal forces and geothermal heat. If Europa or Enceladus harbor life, it might look a lot like what we are finding under Antarctic ice shelves. The Ross ice shelf is the largest ice shelf on Earth. It covers an area of roughly 190,000 square miles. That is slightly bigger than the entire country of France. Beneath this frozen platform lies an ocean that almost no human has ever seen. The water is dark, cold, and deeper than anyone expected. In some places, the seafloor drops to over 3,000 feet below the ice. The shelf itself floats on this hidden ocean, held in place by a few anchor points where the ice runs aground on underwater ridges. The rest is suspended above a void. For over a century, scientists believed the water beneath the Ross ice shelf was calm and mostly lifeless. Early expeditions drilled small holes and lowered basic instruments, finding only cold water and mud. The assumption was that nothing of importance happened in this frozen darkness. That assumption was shattered when modern technology allowed deeper exploration. Robotic submarines equipped with cameras and sensors revealed a landscape beneath the ice that defies easy description. There are underwater mountains, deep trenches, channels carved by currents moving faster than expected. The ice above is not smooth. It has ridges, valleys, and massive keels extending hundreds of feet down into the water like inverted mountain ranges. In some areas, the ice is melting so fast that cavities the size of stadiums have formed. In others, seawater refreezes onto the bottom of the shelf, building strange formations of marine ice. The conditions are alien. The temperature of the water sits at around -2 degrees Celsius. It is kept liquid by salt and pressure. Animals that live here have antifreeze proteins in their blood to prevent ice crystals from forming inside their cells. The currents are tidal, driven by the pull of the moon and the circulation of the Southern Ocean beyond. Warm water occasionally intrudes from the deep ocean, melting the ice from below and triggering changes that ripple through the entire system. Scientists have found life in almost every sample they take from beneath the Ross ice shelf. Bacteria coat the underside of the ice. Fish swim through the water column. Invertebrates crawl along the seafloor. And the deeper the robots go, the more diverse the ecosystem becomes. There are species here that exist nowhere else on Earth. They have evolved in isolation, cut off from sunlight and the rest of the ocean for thousands of years. But what truly terrifies researchers is how little they know about the shelf's stability. The ice is thick, yes, but it is also fragile. It floats on water, anchored only at a few critical points. If warming ocean currents undercut those anchor points, the entire shelf could break free. This has happened before in other parts of Antarctica. The Larsen B ice shelf collapsed in a matter of weeks. The Ross ice shelf is much larger and has been stable for much longer, but the warning signs are appearing. Cracks are forming. Melt rates are increasing. The water temperature is rising, even if only by fractions of a degree. If the Ross ice shelf were to collapse, it would not directly raise sea levels. It is already floating, so its ice is already displacing water. But its collapse would remove a crucial barrier holding back the glaciers on land. Those glaciers would accelerate, pouring ice into the ocean at an unprecedented rate. Sea levels would rise by several feet within decades. Coastal cities around the world would be reshaped. And all of this hinges on an ocean that fewer than a dozen people have ever directly observed. The water beneath Antarctica is the coldest liquid ocean water on Earth. It sits at temperatures that would freeze normal seawater solid. The reason it remains liquid is salt. Antarctic bottom water has a high salinity, which lowers its freezing point to around -2 degrees Celsius. Add the crushing pressure from the ice above, and the freezing point drops even further. This creates a strange environment where water can flow freely, even though it is colder than the ice in your freezer. Scientists measure the temperature with extreme precision because even tiny changes have massive consequences. A shift of half a degree can trigger accelerated melting of the ice shelves. A change of 1 degree can alter ocean currents that affect the entire planet. And the water is getting warmer, not everywhere and not all at once, yet the trend is undeniable. Instruments placed beneath the ice over the past 2 decades show a creeping increase in temperature, especially in West Antarctica. The source of this warming is deep ocean currents. Water from the tropics and mid-latitudes flows south, sinks, and creeps along the ocean floor until it reaches Antarctica. Normally, this water is blocked by the cold Antarctic circumpolar current. But in certain areas, warm water finds a way through. It seeps onto the continental shelf, flows beneath the ice shelves, and begins to melt the ice from below. This process is invisible from the surface. You cannot see it on satellite images. You cannot measure it without sending probes into the water. And until recently, scientists did not know it was happening. The realization came when researchers started comparing ice shelf thickness over time. In some regions, the shelves were thinning far faster than surface melting could explain. Something was eating the ice from underneath. When they finally measured the water temperature beneath those shelves, they found warm layers of water, several degrees above freezing, circulating in contact with the ice. The melting happens in slow motion. The warm water rises and touches the underside of the ice. Heat transfers from the water to the ice. The ice melts, releasing cold fresh water that is lighter than seawater. This fresh water rises, creating a layer of cold water that temporarily shields the ice. But the currents keep bringing in more warm water, and the cycle continues. Over months and years, enormous volumes of ice dissolve into the ocean. The fresh water released by this melting has its own consequences. It alters the salinity of the surrounding ocean, which affects ocean currents. Antarctic bottom water, formed by the sinking of cold, salty water near the ice shelves, is one of the main drivers of global ocean circulation. If the water becomes less salty due to ice melt, it becomes less dense. It sinks more slowly. The circulation weakens. And when the circulation weakens, heat distribution across the planet changes. Weather patterns shift. Marine ecosystems are disrupted. Fisheries collapse. The impact spreads far beyond Antarctica. What makes this process especially frightening is the feedback loop. Warmer water melts more ice. More ice melting releases more fresh water. More fresh water changes the ocean currents. Changed currents bring in even more warm water. The cycle accelerates. Scientists call this a positive feedback loop, though there is nothing positive about it. Once it begins, it is very difficult to stop, and in some parts of Antarctica, it is already well underway. The Thwaites Glacier, the Doomsday Glacier, sits directly in the path of one of these warm water intrusions. Beneath its ice shelf, the ocean is several degrees warmer than it should be. The melting is relentless. Thwaites Glacier in West Antarctica is one of the most closely watched pieces of ice on the planet. Scientists call it the Doomsday Glacier, and the name is not an exaggeration. The glacier is massive. It covers an area roughly the size of Florida. It holds enough ice to raise global sea levels by more than 2 feet if it were to completely collapse. And it is collapsing. Not all at once, yet the process has already begun. What makes Thwaites so dangerous is what lies beneath it. The glacier rests on bedrock that slopes downward toward the interior of Antarctica. This creates an unstable situation. As the front of the glacier melts and retreats, the ice behind it sits in deeper water. Deeper water means more contact with warm ocean currents. More contact means faster melting. Faster melting means more retreat. The cycle feeds itself. Scientists call this marine ice sheet instability. And once it starts, it is almost impossible to reverse. The glacier is also grounded below sea level along most of its base. There is no high ridge holding it in place. The bedrock dips down into a massive basin that extends hundreds of miles inland. If Thwaites loses its grip on the shallow seafloor at its front edge, the entire glacier could begin sliding backward into deeper water. The collapse would take decades, maybe a century, yet the consequences would be catastrophic. Beneath the Thwaites ice shelf, researchers have found something alarming. Warm water is intruding at depths of several hundred feet, flowing in from the open ocean and circulating directly against the underside of the ice. The water temperature in some areas reaches 3 degrees Celsius. That might not sound warm, yet it is 5 degrees warmer than the surrounding seawater. In this environment, that is a blowtorch. The warm water melts the ice at a rate of several feet per year. The ice shelf is thinning. Cracks are forming. Satellite images show the shelf is fracturing in multiple places. Some scientists believe the shelf could disintegrate within the next decade. And when it does, the glacier behind it will lose a critical break. Ice shelves do not just float passively. They push back against the glaciers, on land, slowing their movement toward the sea. Remove the shelf, and the glacier accelerates. Thwaites is already moving faster than it did 20 years ago. Measurements show the glacier is sliding toward the ocean at a rate of over a mile per year in some sections. That is fast for a glacier, and the speed is increasing. What terrifies scientists is not just the glacier itself. Thwaites acts as a plug for the glaciers behind it. If Thwaites goes, it could destabilize the entire West Antarctic ice sheet. That ice sheet contains enough water to raise sea levels by over 10 feet. The timeline for such a collapse is uncertain. Some models suggest centuries. Others suggest it could happen much faster if the right triggers align. Either way, the process has started, and there is no clear way to stop it. Researchers have sent underwater robots beneath the Thwaites ice shelf to study the melting up close. The footage they brought back is haunting. The underside of the ice is not smooth. It is carved into jagged ridges and deep channels, sculpted by the flow of warm water. In some places, the ice is paper thin. In others, massive chunks have already broken away, leaving voids the size of buildings. The robots also found something unexpected: life. Even in this dissolving world, organisms cling to existence. Small invertebrates attached to the ice, fish swimming through the channels, microbes coating every surface. Life endures even as the ice disappears. If Thwaites Glacier collapses, the immediate impact will be a sea level rise of around 2 feet. That alone would redraw coastlines around the world. Low-lying island nations would lose habitable land. Coastal cities would face increased flooding. Storm surges would reach farther inland. Infrastructure built near the water would become unusable. But 2 feet is just the beginning. The real danger comes from what happens next. Thwaites is holding back a much larger volume of ice in the West Antarctic ice sheet. When it goes, that ice will follow. Scientists estimate the full collapse of the West Antarctic ice sheet would raise sea levels by 10 to 12 feet. This would not happen overnight. The process could take a century or more. Yet even a partial collapse within the next 50 years would be catastrophic. A sea level rise of just 3 feet would displace over 100 million people worldwide. Cities like Miami, New Orleans, and Shanghai would face permanent flooding. Entire neighborhoods would be abandoned. Infrastructure would need to be rebuilt farther inland. The economic cost would run into the trillions of dollars, and that is a conservative estimate. A rise of 6 feet would be far worse. Major cities would lose entire districts. Airports built on coastal land would go underwater. Ports would need to be relocated. Farmland in river deltas would be inundated with salt water, destroying crops and contaminating freshwater supplies. Countries like Bangladesh, which sits mostly at or near sea level, would see a significant portion of their land disappear beneath the waves. The human cost would be staggering. At 10 feet, the map of the world changes. Large parts of Florida vanish. The Netherlands struggles to hold back the ocean despite its advanced dike systems. London, New York, Tokyo, and dozens of other major cities face the choice of building massive seawalls or retreating inland. The investment required to adapt to this new reality would strain even the wealthiest nations. Poorer countries would simply not have the resources to protect their populations. Climate refugees would number in the hundreds of millions. What makes this especially cruel is the timeline. The people alive today will not see the worst of it. The children being born now will. The decisions we make in the next decade will determine how much ice melts and how fast. Yet the political will to act remains weak. The problem feels distant, abstract, easy to ignore. Meanwhile, beneath the ice in Antarctica, warm water continues to flow. The glaciers continue to thin. The cracks continue to spread. Scientists monitoring Thwaites release new studies every few months, each one more alarming than the last. The glacier is melting faster than previous models predicted. The instability is more advanced than they thought. The timeline for collapse keeps shrinking, and there is nothing anyone can do to stop it. We cannot refreeze the glacier. We cannot block the warm water from reaching it. We cannot reverse the process that has already begun. The only option is to slow the rate of warming by reducing greenhouse gas emissions. Even that will not save Thwaites. The glacier is already doomed. But it might buy time for other parts of Antarctica. It might prevent additional glaciers from crossing the point of no return. It might mean the difference between 10 feet of sea level rise and 20. The ocean beneath Antarctica does not care about politics or economics. It responds to physics. Warm water melts ice. Melting ice raises sea levels. And the warming is not stopping. In 2019, a team of researchers sent a robotic submarine beneath the Thwaites ice shelf. The robot was shaped like a torpedo, bright orange, packed with cameras and sensors. Its mission was simple: explore the underside of the ice and see what was happening in the melt zone. The robot descended into the dark water and began transmitting footage back to the research vessel on the surface. What it filmed was both beautiful and terrifying. The underside of the ice shelf looked like an alien landscape. Massive ridges of ice hung down into the water, some reaching depths of over 600 feet. Between the ridges were smooth channels carved by flowing water. The ice glowed faintly in the robot's lights, a pale blue that seemed to pulse with an inner luminescence. The robot navigated through narrow gaps and wide caverns, measuring temperature, salinity, and current speed as it went. The data confirmed what scientists feared. Warm water was flowing directly against the ice in powerful currents. The temperature readings spiked in certain areas, indicating pockets of water several degrees above freezing. The melting was not uniform. In some places, the ice was dissolving rapidly. In others, it remained relatively stable. The pattern suggested that the warm water was following specific pathways, channels carved into the seafloor that funneled the flow directly to the most vulnerable parts of the ice. But the footage also revealed something unexpected: life. Everywhere the robot looked, there were signs of living organisms. Small crustaceans darted past the camera. Jellyfish drifted through the water column. Fish hovered near the ice, seemingly unbothered by the cold or the darkness. The ice itself was coated in a thin layer of microbes, a living film that clung to every surface. How these creatures survived in such an environment remained a mystery. There was no sunlight, no photosynthesis. The water was barely above freezing. Yet they were not just surviving, they were thriving. The robot collected water samples that later revealed a complex food web, based on bacteria and organic material carried in by ocean currents. The larger animals fed on smaller ones, which fed on microbes, which fed on chemicals and nutrients in the water. It was a complete ecosystem functioning in near total darkness. Other expeditions sent robots to different ice shelves and found similar results. Beneath the Rona ice shelf, cameras captured footage of sponges attached to rocks on the seafloor. Sponges are filter feeders. They draw in water and extract nutrients. Finding them in this environment meant there was enough food in the water to sustain them, even hundreds of miles from the open ocean. Beneath the Filchner ice shelf, researchers found dense clusters of sea anemones, their tentacles waving in the slow current. These creatures are typically found in shallower waters where food is more abundant. Yet here they were, thriving in one of the most extreme environments on the planet. The robots also filmed something disturbing. In several locations, they found chunks of ice that had recently broken away from the shelf, still fresh and jagged. These pieces had fallen into the water and were slowly drifting with the current. Some were the size of cars. Others were as large as houses. The frequency of these ice falls suggested that the shelves were fracturing more often than scientists realized. Each piece that broke away weakened the overall structure. Each crack that formed made the next break more likely. The robots operated for only a few hours at a time. Battery life in the extreme cold was limited. Retrieving the machines was difficult and risky. Yet every mission brought back footage that reshaped our understanding of what exists beneath the ice. And every mission raised the same question: what else is down there that we have not seen yet? The creatures living in Antarctic waters are strange in ways that go beyond simple adaptation. They are huge, far larger than their relatives in warmer oceans. Scientists call this phenomenon polar gigantism, and it occurs in both the Arctic and Antarctic, though it is more pronounced in the south. Sea spiders in temperate waters are typically the size of a small coin. In Antarctica, they can grow to the size of a dinner plate. Their legs span over a foot in some species. They move slowly across the seafloor, feeding on soft-bodied invertebrates and organic debris. Their bodies are so large that their internal organs extend into their legs because there is not enough room in their central body. Isopods, a type of crustacean related to pillbugs, also reach enormous sizes in Antarctic waters. In most oceans, they are less than an inch long. Around Antarctica, some species grow to over a foot in length. They look like oversized versions of the insects you might find under a rock in your backyard, except they live in freezing water under miles of ice. Jellyfish in Antarctic waters can reach diameters of several feet, their tentacles trailing dozens of feet behind them as they drift through the dark. Amphipods, tiny shrimp-like creatures that are usually smaller than your fingernail, grow to the size of your fist in the coldest Antarctic waters. And it is not just invertebrates. Some fish species also show signs of gigantism, though the effect is less dramatic. Why does this happen? The leading theory has to do with oxygen. Cold water holds more dissolved oxygen than warm water. In the freezing temperatures around Antarctica, oxygen levels are exceptionally high. This allows animals to grow larger without needing more efficient respiratory systems. Their cells can get the oxygen they need, even at greater sizes. Metabolism also plays a role. Cold water slows metabolic rates. Animals move more slowly, grow more slowly, and live longer. A slower metabolism means less energy is needed to maintain body functions, which allows more energy to be directed toward growth. Over many generations, this leads to larger body sizes. But there is a trade-off. Larger size means slower movement. In a predator-rich environment, this would be a fatal disadvantage. Yet under the Antarctic ice, predators are scarce. The ecosystem is food limited, which means competition is less intense. Animals can afford to be slow because there is less pressure to escape or chase prey. The isolation also matters. Many of these species have been evolving in Antarctica for millions of years, cut off from gene flow from warmer regions. They have adapted to an environment that is stable in some ways and extreme in others. The temperature barely changes. The seasons bring shifts in ice cover and light. Yet under the ice shelves, darkness is constant. Evolution in this environment has favored traits that suit a slow, cold, dark world. But gigantism comes with risks. Larger, animals need more food. In an ecosystem where food is already scarce, this creates vulnerability. If conditions change, if currents shift and bring less nutrients, the giant species would be the first to suffer. They cannot adapt quickly. Their slow reproduction rates mean populations recover slowly from any decline. Climate change is already altering the Antarctic ecosystem. Warming water is bringing new species south. Faster-growing, smaller animals from temperate regions are starting to appear in areas that were previously too cold for them. These newcomers reproduce quickly and compete for resources. The slow-growing giants are at a disadvantage. Scientists have documented shifts in species composition in some Antarctic regions over the past 2 decades. The balance is changing, and once it tips, it may not tip back. The giants of the Antarctic Ocean are living fossils in a sense. They represent an evolutionary path that flourished in isolation. They are a window into how life adapts when conditions remain stable for millions of years. And they are a warning about what happens when that stability breaks. In 2016, scientists using ice-penetrating radar discovered something beneath the Antarctic ice sheet that they did not expect. A canyon system. Not small channels or cracks in the bedrock, yet deep, wide valleys carved into the rock itself. Some of these canyons are over a mile deep and stretch for hundreds of miles. They lie hidden beneath ice that is itself over a mile thick in places. No human has ever seen them directly. We know they exist only because of the radar signals that bounce back from the bedrock below. The largest of these canyons runs beneath the Transantarctic Mountains and connects the east and west Antarctic ice sheets. It is deeper than the Grand Canyon and longer than any river valley in Europe. Scientists believe it was carved by water, either from ancient rivers that flowed millions of years ago when Antarctica was warmer, or by meltwater flowing beneath the ice sheet today. The discovery of these canyons changed the way scientists think about ice sheet stability. The shape of the bedrock beneath the ice determines how the ice moves. Flat bedrock allows ice to spread slowly and evenly. Valleys and canyons funnel ice into narrow channels where it flows faster. The faster the ice flows, the more quickly it reaches the ocean. And the more ice that reaches the ocean, the faster sea levels rise. The canyon systems also affect how water moves beneath the ice. Subglacial rivers flow along the bedrock, carrying meltwater from the interior of the ice sheet toward the coast. These rivers follow the topography of the bedrock, just like rivers on the surface follow the shape of the land. The canyons act as highways for this water, channeling it into specific outlets. Where the water exits, it can lubricate the base of the ice, causing the ice to slide more easily toward the sea. Some of the canyons are filled with subglacial lakes. These lakes sit in the deepest parts of the valleys, trapped between the ice above and the bedrock below. They are connected by the river systems, forming a network that scientists are only beginning to map. Water levels in these lakes rise and fall as water flows in and out, sometimes draining completely and then refilling over the course of months or years. The movement of water through this hidden system has direct effects on the ice above. When a lake drains, the ice above it sinks. When it refills, the ice rises. Satellites can detect these changes in elevation, which is how scientists first realized the lakes were there. But the implications go deeper. The flow of water beneath the ice affects its speed and stability. Changes in the bedrock topography can accelerate or slow the movement of entire glaciers. And we are still discovering new features. Every radar survey reveals previously unknown valleys, ridges, and basins. The bedrock of Antarctica is one of the least known landscapes on Earth, despite being covered by the largest ice sheet on the planet. Some scientists believe there are features beneath the ice that rival anything we see on the surface anywhere else in the world. Mountain ranges buried under ice, valleys deeper than any we have explored, plains that stretch for hundreds of miles without a single human footprint because no human can reach them. And all of it is hidden, locked away beneath ice that has been there for millions of years. But the ice is not permanent. It is melting. And as it melts, the landscape beneath is starting to influence the speed and direction of that melting in ways we are only beginning to understand. In 2017, researchers drilling into the Antarctic ice sheet pulled up a core sample that contained something extraordinary: fossilized pollen. The pollen came from plants that grow in tropical and subtropical climates. Palms, ferns, flowering trees. The pollen was found in sediment that had been buried under the ice for over 90 million years. This was direct evidence that Antarctica was once covered in forests. Not sparse tundra or hardy shrubs, yet lush jungle. The kind of environment you would expect to find near the equator, not at the bottom of the world. The discovery was not entirely surprising. Scientists have known for decades that Antarctica was not always frozen. Plate tectonics shows that the continent was once part of the supercontinent Gondwana, positioned much farther north than it is today. Over millions of years, it drifted south, eventually settling over the South Pole. But even after it reached its current position, the climate remained warm enough for forests to thrive. This was during the Cretaceous period, when dinosaurs roamed the Earth and global temperatures were much higher than today. There was no ice at the poles, sea levels were hundreds of feet higher, and Antarctica was green. Fossil evidence supports this. Paleontologists have found fossilized wood, leaves, and even dinosaur bones in Antarctica. The bones belong to species that lived in forested environments, not frozen wastelands. There were herbivorous dinosaurs that fed on plants, carnivores that hunted them, flying reptiles that nested in trees. The ecosystem was complex and thriving. But then, the climate changed. Around 34 million years ago, the Earth began to cool. Ocean currents shifted. The Antarctic circumpolar current formed, isolating the continent from warmer waters to the north. Ice began to accumulate. At first, it was seasonal. Then it became permanent. Glaciers formed in the mountains and began to spread. Within a few million years, the entire continent was buried under ice. The forests died. The animals went extinct or migrated north. The rivers froze. The lakes turned to ice. And Antarctica became the frozen desert it is today. The ice that covers the continent now is up to 3 miles thick in some places. Has been there for millions of years, preserving the landscape beneath like a time capsule. Beneath that ice lies a record of what Antarctica once was. Fossilized forests, ancient riverbeds, volcanic rock from eruptions that happened when the continent was still geologically active. And buried in the sediment are clues to how the transition happened. Scientists study these clues to understand how ice sheets form and collapse. The transition from jungle to icehouse did not happen overnight. It took millions of years, but once it started, it accelerated. Feedback loops kicked in. Ice reflects sunlight, which cools the planet further, which causes more ice to form. The process feeds itself until a new equilibrium is reached. Today, we are watching the reverse process. The ice is melting. The planet is warming. And the same feedback loops that caused Antarctica to freeze are now working in the opposite direction. Melting ice exposes darker rock and water, which absorbs more sunlight, which causes more warming, which melts more ice. The cycle accelerates. Some scientists believe that if current warming trends continue, Antarctica could eventually return to a state similar to what it was millions of years ago. Ice-free, forested, warm. But that transformation would take thousands of years at least, possibly tens of thousands. In the meantime, the melting ice will raise sea levels by dozens of feet, reshaping coastlines and displacing billions of people. The fossils buried beneath the ice are a reminder that nothing is permanent. Continents move, climates change, ice sheets come and go. What seems stable and eternal is actually fragile and temporary. Antarctica was a jungle once. It could be again. But the transition will not be gentle, and it will not be quick. And the ocean beneath the ice, the hidden world we are only now beginning to explore, holds the keys to understanding how fast that change will come. Ancient ferns and palm trees once thrived where now only ice exists. Scientists discovered those fossils embedded in rock, proof of a warmer world that vanished millions of years ago. Yet something else survived that transition. Something far stranger than fossilized leaves. Deep within the ice itself, locked in suspended animation for longer than human civilization has existed. Microorganisms still cling to life. In 2013, researchers drilling through half a mile of Antarctic ice pulled up water samples from Lake Whillans, a body of liquid water trapped beneath the frozen continent. They expected sterility. They found a thriving ecosystem. Nearly 4,000 different types of microbes existed in water that had been sealed off from the atmosphere for hundreds of thousands of years. The organisms weren't merely surviving. They were metabolizing, reproducing, adapted to conditions that would kill almost anything else on Earth. Some of these microbes process chemicals rather than sunlight for energy, feeding on minerals dissolved from the rock beneath the ice. Others have cellular structures never documented before, biology shaped by isolation and extreme cold into forms science is still trying to understand. The implications stretch far beyond Antarctica. If life persists in liquid water beneath miles of ice on Earth, then Europa suddenly seems less alien. Jupiter's moon, locked in ice, thicker than any glacier on our planet, hides an ocean estimated to contain twice as much water as all of Earth's seas combined. For decades, scientists wondered if such an ocean could support life. Antarctica provides the answer. Confirmed observations show that life doesn't just endure in these environments. It finds pathways we never anticipated. The microbes beneath Antarctic ice survive temperatures that hover just above freezing, crushed under pressure from ice above, cut off from any connection to the sun. They represent a blueprint. If biology can flourish under Antarctic ice sheets, then Europa's hidden ocean may not be the dead zone researchers once assumed. Some of the Antarctic microbes metabolize sulfur compounds, the same chemicals detected in geysers that erupt from cracks in Europa's ice crust. The comparison isn't speculation anymore. It's a working model for astrobiology. Space agencies now study Antarctic organisms to design life detection instruments for future missions to icy moons. The microbes teach us what to look for, which chemical signatures indicate biology versus geology. They prove that liquid water plus chemical energy equals potential for life, regardless of how far from the sun that water exists. Yet these organisms carry another message, one that should unsettle anyone paying attention. They've remained frozen in ice for time frames that dwarf human history. Some samples contain microbes that entered suspended animation during the last ice age, when woolly mammoths still walk the earth. Others date back millions of years, locked in ice since before our species evolved, and they wake up. When ice melts, or when drill bits bring them into contact with liquid water, their cellular machinery resumes. Metabolism restarts. They continue lives interrupted by eons of frozen darkness. This resilience means something profound. Life that can pause for millions of years and resume without missing a beat represents biology utterly unlike the fragile ecosystems we know. It suggests that freezing isn't death, it's dormancy, which raises an uncomfortable question. As Antarctic ice melts, what else might wake up? Europa orbits Jupiter in just under 4 days, racing through radiation intense enough to kill a human in minutes. The moon's surface temperature never rises above negative 260 degrees Fahrenheit. Nothing lives on that frozen exterior. Yet beneath an ice shell estimated between 10 and 15 miles thick, an ocean exists. We know this because Jupiter's gravity flexes Europa like a stress ball, creating friction that generates heat. That heat keeps water liquid despite the moon's distance from the sun. Spacecraft have detected what appears to be water vapor erupting from cracks in the ice, geysers that spray ocean material into space where instruments can analyze it. The chemistry looks startlingly familiar. Salts, minerals, compounds similar to those found in Earth's oceans, including beneath Antarctic ice. The parallel isn't coincidental. Both environments feature liquid water sealed beneath thick ice, isolated from atmospheric contact, dependent on chemical rather than solar energy. Both exist in perpetual darkness. Both experience crushing pressure. Antarctica's subglacial lakes provide the closest analog we have to conditions on Europa. Scientists studying Lake Vostok, buried under more than 2 miles of ice, discovered microbial life adapted to exist without photosynthesis, feeding instead on minerals dissolved from bedrock below. The organisms use chemical gradients the way plants use sunlight, extracting energy from reactions between water and rock. Europa likely experiences similar chemistry. The moon's rocky core sits in direct contact with its buried ocean. Tidal forces from Jupiter create friction, heating that core and potentially driving volcanic activity on the ocean floor. If Antarctica's subglacial microbes can thrive on chemical energy from rock, Europa's ocean could support similar biology. Confirmed observations show that hydrothermal vents exist on Earth's ocean floors, cracks in the crust, where superheated water rich in minerals spews into the sea. Life clusters around these vents in staggering abundance despite sunlight never reaching those depths. If Europa has an active core, it likely has vents too. The connection runs deeper than chemistry. Antarctica's hidden ocean teaches us about survival in extreme isolation. The microbes there have evolved for millions of years cut off from surface ecosystems, developing completely independent food webs. Europa's ocean, if it harbors life, would represent isolation on a scale that makes Antarctic lakes look connected. Any organisms there would have evolved separately from Earth biology for the entire history of the solar system. Yet the fundamental equations might be identical. Liquid water plus chemical energy plus geological activity equals potential for life. Antarctica confirms this formula works. Europa offers a chance to test whether it applies beyond our planet. Space agencies now design missions specifically to drill through Europa's ice and sample the ocean beneath. The technology comes directly from Antarctic research. The same drill bits that punch through miles of glacial ice to reach Lake Whillans will be adapted for use on a moon 400 million miles away. Engineers test prototypes in Antarctic conditions because nowhere else on Earth matches Europa's environment so closely. The ice thickness, the subglacial ocean, the isolation, the chemistry, even the radiation levels at certain Antarctic sites mirror what spacecraft will encounter on Europa. If we find life there, it will be because Antarctica showed us where to look. The frozen ocean beneath our own southern continent stopped being just a terrestrial mystery. It became a window into alien worlds. Every microbe recovered from Antarctic ice, every chemical signature detected in subglacial water, every adaptation to extreme cold and darkness tells us something about what might swim in Europa's hidden sea. The question isn't whether life could exist there anymore. Antarctica answered that. The question now is whether it does. The ice conceals more than ancient microbes and hidden oceans. Beneath the western Antarctic ice sheet, under thousands of feet of frozen water compressed into solid mass, the ground itself burns. In 2017, scientists analyzing seismic data detected something impossible. Heat signatures rose from deep beneath the ice, far too intense to come from geothermal background radiation. The source was volcanic. Antarctica sits atop one of the largest volcanic provinces on Earth, a feature researchers only recently confirmed existed. The region contains at least 138 volcanoes, though the true number likely exceeds that by dozens more still undiscovered beneath the ice. Some of these volcanoes stand taller than the Alps. Others sprawl across areas larger than entire European countries, and they're not all extinct. Mount Erebus, located on Ross Island, ranks as the southernmost active volcano on the planet. It maintains a permanent lava lake in its summit crater, molten rock exposed to air, despite being surrounded by one of the coldest environments on Earth. Scientists have recorded eruptions from Erebus regularly since its discovery over a century ago. The volcano produces gases that interact with Antarctic air to create ice towers around its summit. Frozen chimneys that vent volcanic heat into the atmosphere. Erebus alone isn't the concern. It sits on an island with minimal ice cover. The real threat lies beneath the western ice sheet, where volcanic activity occurs under miles of glacial weight. When those volcanoes erupt, the ice above them melts from below. In 2014, researchers detected a massive heat source beneath the Thwaites Glacier, one of Antarctica's most unstable ice formations. The heat came from volcanic activity scientists hadn't known existed. Temperature readings showed areas beneath the ice reaching several hundred degrees, hot enough to melt thousands of tons of ice per hour. That meltwater doesn't evaporate. It flows along the bedrock beneath the glacier, lubricating the ice sheet's contact with solid ground. Glaciers move faster when meltwater reduces friction between ice and Earth. Volcanic heat accelerates that process dramatically. Some models suggest that volcanic activity beneath western Antarctica contributes more to ice sheet instability than atmospheric warming. The ice sits on top of an active geological system that generates its own melting from within. Scientists debate how much volcanic heat affects overall ice loss. Estimates vary because measuring volcanic activity beneath miles of ice presents obvious challenges. Seismic sensors can detect tremors, but distinguishing between tectonic shifts and actual eruptions requires data that's difficult to collect in Antarctica's interior. Some researchers believe a major eruption occurred beneath the ice sheet within the last 10,000 years, melting enough ice to create a cavity larger than Manhattan beneath the glacier. Others suggest continuous low-level volcanic activity provides steady heat that compounds with atmospheric warming to destabilize ice far faster than climate models predict. Either way, the confirmed presence of active volcanoes beneath Antarctic ice means the continent's behavior isn't purely a function of air temperature and snowfall. There's an internal engine, one that operates regardless of what happens in the atmosphere above. This makes prediction incredibly difficult. Climate models can estimate how much ice will melt based on projected temperature increases. But if a volcano erupts beneath a major glacier, it could trigger ice loss equivalent to decades of atmospheric warming in a matter of months. The ice sheet becomes unpredictable when the ground beneath it can spontaneously heat up. Volcanic gases complicate the equation further. When lava meets ice, the resulting steam carries dissolved minerals and gases into the meltwater. Some of these compounds act as antifreeze, lowering the temperature at which water freezes and creating pockets of liquid where ice should exist. These pockets destabilize glaciers from within, creating voids that cause ice to fracture and collapse. Antarctica's volcanic system represents a wild card that climate science is only beginning to account for. The frozen continent isn't geologically stable. It's an active landscape where fire and ice meet miles beneath the surface, locked in a relationship that determines how quickly the ice above survives or disappears. Antarctica exists in isolation unlike anywhere else on Earth. The continent sits alone at the bottom of the world, separated from other landmasses by the most powerful ocean current that has ever existed. The Antarctic circumpolar current wraps around the frozen continent like a liquid barrier, flowing east in a loop that never touches land. The current moves 140 million cubic meters of water per second. To put that in perspective, that's more than 100 times the flow of all rivers on Earth combined. The current carries more water than the Atlantic Gulf Stream, the Pacific Kuroshio, and every other major ocean current added together. Nothing else in Earth's oceans approaches its scale. The current exists because of Antarctica's unique position. No other continent sits entirely within polar latitudes, surrounded by uninterrupted ocean. With no land to block its path, the current flows continuously around the globe, driven by relentless westerly winds that circle the pole without obstacle. The wind pushes water eastward, and the water keeps flowing because there's nowhere for it to stop. This isolation serves a purpose. The Antarctic circumpolar current acts like a moat, thermally isolating the frozen continent from warmer waters to the north. Ocean currents from the tropics and mid-latitudes can't penetrate the circumpolar flow easily. The current creates a boundary, a thermal fence that keeps Antarctica colder than it would otherwise be. Scientists believe the current formed roughly 34 million years ago, when Antarctica finally separated from South America, creating the Drake Passage. Before that opening existed, ocean circulation couldn't flow uninterrupted around the pole. Once the passage formed, the current spun up and Antarctica's climate changed dramatically. Temperatures plummeted, ice sheets expanded. The continent transformed from a partially forested landscape into the frozen wasteland we know today. The current didn't just isolate Antarctica thermally, it isolated the continent biologically as well. Marine species from warmer waters can't easily cross the temperature barrier the current creates. Antarctic fish, seals, and other marine life evolved in isolation, developing unique adaptations to extreme cold. Some fish species produce antifreeze proteins in their blood to survive temperatures that would kill related species from other oceans. The isolation works both ways. Cold water from Antarctica can't easily flow north, past the current either. Instead, it sinks. Antarctic water is the densest ocean water on Earth, heavy with cold and high salinity. When it sinks, it flows along the ocean floor, spreading northward beneath the circumpolar current, and eventually into every ocean basin on the planet. This creates a conveyor belt, a global circulation system where Antarctic water drives currents that affect weather patterns and climate thousands of miles away. The current's speed matters more than most people realize. It flows faster than a human can swim, creating ocean conditions that make navigation treacherous. Ships crossing from South America to Antarctica must pass through the Drake Passage, widely considered the roughest ocean crossing on Earth. Waves in the Drake regularly exceed 30 feet. Storms appear with minimal warning. The same winds that drive the circumpolar current create weather patterns that shift unpredictably. Sailors call these latitudes the screaming 60s because the wind never stops. Climate change is altering the current in ways scientists are only beginning to understand. The westerly winds that drive the flow have intensified over recent decades, which theory suggests should strengthen the current. A stronger current means more thermal isolation, which should protect Antarctic ice from warming ocean waters. Yet, observations show the opposite happening. Warmer water is reaching the continent's ice shelves despite the current's existence. The mechanisms behind this remain debated. Some researchers believe the current is shifting southward, moving closer to Antarctica and allowing warmer water to penetrate at depth. Others suggest the current itself is warming, meaning the thermal barrier it provides has become less effective. Either way, the current that once protected Antarctica so effectively for millions of years may be losing its ability to keep the frozen continent isolated. The question now is how fast that change occurs and whether anything can slow it down. The most powerful current on Earth, it turns out, isn't invincible. What happens in Antarctica doesn't stay in Antarctica. The frozen continent manufactures water so cold and dense that it sinks to the ocean floor and flows across the entire planet. This water, called Antarctic bottom water, drives global ocean circulation in ways that affect weather patterns, marine ecosystems, and climate stability thousands of miles from the ice. The process begins along Antarctica's coastline, particularly in the Weddell and Ross Seas. Here, sea ice forms each winter, freezing the ocean's surface. When salt water freezes, it expels most of its salt into the surrounding liquid. This makes the unfrozen water nearby saltier and therefore denser than normal seawater. Combine that high salinity with temperatures hovering just above freezing, and you get the densest water in any ocean. Density makes it sink. Antarctic bottom water plunges toward the ocean floor and spreads outward from the continent, flowing north along the bottom of the Atlantic, Pacific, and Indian Oceans. This water eventually reaches the equator and beyond, creeping along the seafloor beneath warmer tropical currents above. Scientists have traced Antarctic bottom water as far north as the Aleutian Islands in the Pacific and into the North Atlantic near Greenland. The water takes centuries to complete this journey. A molecule of water that sinks off Antarctica today might not reach the North Atlantic for 500 years or more. Yet the flow never stops. Antarctica constantly produces new bottom water, driving a conveyor belt that circulates the ocean from pole to pole. This circulation matters because it distributes heat and nutrients globally. Warm water from the tropics flows toward the poles along the ocean's surface, carrying heat poleward. When that water reaches polar regions, it cools, sinks, and returns toward the equator at depth. This overturning circulation moderates global temperatures by transporting heat from regions that receive excess solar energy to regions that receive too little. Without it, the tropics would be far hotter and polar regions far colder. Antarctic bottom water also carries oxygen from the atmosphere into the deep ocean. When water at the surface freezes, the surrounding liquid absorbs oxygen from the air before sinking. That oxygenated water then travels along the ocean floor, sustaining deep-sea ecosystems that would otherwise suffocate. Many deep ocean species depend on this oxygen supply. If Antarctic bottom water formation slows or stops, oxygen levels in the deep ocean could decline catastrophically. Scientists monitoring the Southern Ocean have detected troubling changes. The volume of Antarctic bottom water being produced has decreased measurably over the past several decades. The water itself is getting warmer and less dense, which means it doesn't sink as readily or flow as far. Some measurements show Antarctic bottom water production has declined by as much as 1/3 since the 1970s. The cause appears linked to ice shelf melting. As glaciers and ice shelves deteriorate, fresh water pours into the Southern Ocean. Fresh water is less dense than salt water, so this influx dilutes the ocean's salinity near Antarctica. Lower salinity means lower density, which reduces the water's tendency to sink. If enough fresh water enters the Southern Ocean, it could shut down Antarctic bottom water formation entirely. The consequences would extend far beyond Antarctica. Ocean circulation models suggest that a significant slowdown in bottom water production would disrupt global current systems within decades. The Gulf Stream, which keeps Europe warmer than its latitude suggests it should be, depends partly on the pool of sinking water in polar regions. If Antarctic bottom water weakens, the entire Atlantic overturning circulation could slow, potentially triggering climate shifts across the northern hemisphere. Marine ecosystems would suffer as well. Deep sea oxygen levels would drop, creating dead zones where currently thriving communities exist. Fish stocks in areas far from Antarctica could collapse as the nutrient distribution that sustains them breaks down. The water sinking off Antarctica today carries nutrients that will fertilize fisheries in the north in Pacific 50 years from now. Interrupt that flow and you interrupt food webs across multiple oceans. Antarctica's hidden ocean doesn't just terrify scientists because of what it contains. It terrifies them because of what it controls. The cold water sinking beneath the ice shelves drives systems that regulate climate and marine life across the entire planet. And that system is changing faster than anyone predicted. High above Antarctica, in the thin air of the stratosphere, a hole opens each spring. For weeks, the ozone layer over the frozen continent thins to dangerous levels, allowing ultraviolet radiation from the sun to penetrate more intensely than anywhere else on Earth. The hole forms because of chemical reactions between ozone molecules and industrial compounds released decades ago. Scientists discovered the phenomenon in the 1980s and have monitored it ever since. The ozone hole matters for reasons beyond radiation. It changed wind patterns over Antarctica in ways that affect the hidden ocean beneath the ice. The stratosphere and the ocean seem disconnected, separated by miles of atmosphere and thousands of feet of ice. Yet the ozone hole created a chain reaction that reached all the way to the seafloor. When ozone in the stratosphere thins, it absorbs less ultraviolet radiation. That changes temperature gradients in the atmosphere above Antarctica. Cooler stratospheric temperatures alter the behavior of the polar vortex, a circulation of winds that spins around the continent during winter. As the vortex strengthens, it pulls the westerly winds that circle Antarctica into a tighter, faster pattern. Those stronger winds drive the Antarctic circumpolar current harder, increasing the current's speed and changing how water mixes at different depths. Faster winds also push surface water northward more aggressively. When surface water moves away from Antarctica, deeper water rises to replace it, a process called upwelling. This upwelling brings warmer subsurface water toward the ice shelves, water that had been safely isolated at depth. The warmer water melts the underside of floating ice shelves, thinning them from below. Scientists have documented this process occurring along the Amundsen Sea coastline, where some of Antarctica's most vulnerable glaciers meet the ocean. The ozone hole made the winds stronger. The winds made the current faster. The faster current brought warmer water to the ice, and the ice started melting faster than climate models had predicted, based on atmospheric temperature alone. The connection took years to confirm. Researchers had to link changes in the stratosphere to shifts in ocean circulation, then connect ocean circulation to ice shelf melting rates. The data eventually showed a clear pattern. Years when the ozone hole was particularly severe corresponded with years when ice shelf melting accelerated. The relationship wasn't immediate because ocean circulation responds slowly to atmospheric forcing, but the trend became undeniable. The ozone hole was affecting Antarctica's ice, not through direct radiation or surface heating, but by altering winds that changed ocean currents that brought warmer water to the ice. The international ban on ozone-depleting chemicals, enacted in the late 20th century, has allowed the ozone hole to begin recovering. Satellite measurements show the hole shrinking gradually over recent decades. Scientists expect it to close completely sometime in the late 21st century. As the ozone layer recovers, stratospheric temperatures should normalize. That should weaken the polar vortex, which should slow the westerly winds, which should reduce upwelling of warm water near Antarctica's ice shelves. Theory suggests that ozone recovery might actually slow Antarctic ice loss by reversing the wind changes that brought warmer water to the ice in the first place. Yet climate change complicates this hopeful scenario. Even if the ozone hole closes and winds return to historical patterns, the ocean itself is warming. The subsurface water that upwells near Antarctica is warmer now than it was 50 years ago, regardless of how fast winds push it around. So even if wind patterns normalize, the water reaching the ice will still be warmer than it used to be. The ozone hole taught scientists an important lesson about Antarctica. The continent doesn't exist in isolation, despite the circumpolar current that surrounds it. Changes in the atmosphere above affect the ocean below, which affects the ice, which affects sea level globally. Everything connects. A chemical released from a refrigerator in New York could eventually contribute to ice shelf melting in the Amundsen Sea through a chain of atmospheric and oceanic reactions. The system is more interlinked than anyone realized before the ozone hole appeared. Now, as scientists watch the hole slowly heal, they're left wondering what other invisible connections exist. What other atmospheric changes might be affecting the hidden ocean beneath Antarctic ice in ways we haven't yet detected? The ozone hole was discovered by accident when scientists happened to look at the right data. What else should we be looking for? The ice doesn't belong to anyone, officially. 7 nations claim portions of Antarctic territory, their overlapping sectors drawn like slices of pie radiating from the South Pole. Argentina, Chile, the United Kingdom, Norway, France, Australia, and New Zealand all assert sovereignty over parts of the frozen continent. The United States and Russia reserve the right to make claims, but haven't formally done so. Most of the world ignores these claims. International law considers Antarctica a global commons, territory held in trust for all humanity. The Antarctic Treaty, signed in 1959, froze all territorial claims and dedicated the continent to peaceful scientific research. For over 60 years, that treaty has kept Antarctica free from military installations, nuclear weapons, and resource exploitation. It's one of the most successful international agreements ever created. Yet cracks are appearing in the consensus. As satellite surveys reveal the full extent of mineral wealth beneath Antarctic ice, nations that once seemed content with scientific cooperation have grown more assertive about their claims. The resources are staggering. Geological surveys suggest Antarctica contains massive deposits of coal, iron ore, copper, and rare earth elements. The surrounding ocean floor likely holds significant oil and natural gas reserves. Estimates vary, but some projections suggest the Ross Sea region alone could contain enough oil to rival reserves in the North Sea. Other areas may hold deposits of platinum, gold, and uranium. For now, the Antarctic Treaty prohibits mining and drilling. Protocol 6, enacted in 1991, banned resource extraction indefinitely. But indefinitely doesn't mean forever. The ban can be lifted if all treaty signatories agree. And with global demand for rare earth elements skyrocketing and easily accessible deposits elsewhere running low, pressure to reconsider that ban is building. China has increased its Antarctic presence dramatically over the past 2 decades, building research stations and expanding its icebreaker fleet faster than any other nation. Officials claim scientific interest, and much of the research conducted is legitimate. Yet the scale of investment suggests motives beyond pure science. China now operates 5 permanent research stations in Antarctica, more than most treaty signatories. Its icebreaker fleet can reach parts of the continent that remain inaccessible to other nations. Russia has similarly expanded its Antarctic infrastructure, renovating old Soviet-era bases and establishing new facilities in remote regions. Both nations have histories of resource extraction in extreme environments, expertise that would translate directly to Antarctic operations if the mining ban were ever lifted. The United Kingdom, Argentina, and Chile maintain overlapping claims to the Antarctic Peninsula, a region that is warming faster than almost anywhere else on Earth. As ice retreats, previously inaccessible areas become easier to survey and potentially exploit. All three nations have reinforced their Antarctic presence in recent years, conducting sovereignty patrols and building new facilities in disputed areas. Tensions occasionally flare. In 2020, Argentina protested British military exercises near Antarctic research stations. Chile objected to Argentine construction projects in areas both nations claim. The disputes remain non-violent, constrained by treaty obligations, but the rhetoric has grown sharper. Some politicians in claiming nations now argue that Antarctica's resources should belong to the countries with historical stakes, rather than being held in global trust. Environmental groups warn that any move toward resource exploitation would devastate Antarctic ecosystems. Mining operations would require massive infrastructure, roads across ice, power generation, waste disposal, all in one of the most fragile environments on Earth. Oil drilling in the Southern Ocean would risk spills in waters where cold temperatures make cleanup nearly impossible. Even if extraction technology improves, the environmental cost seems impossible to justify. Yet economic pressure rarely yields to environmental arguments when resources become scarce enough. Rare earth elements are critical for electronics, renewable energy technology, and military hardware. As global supplies tighten, Antarctica's deposits become harder to ignore. Some analysts predict that by mid-century, the economic value of Antarctic minerals will outweigh the political will to keep them off limits. The question isn't whether nations want access to Antarctic resources. They do. The question is whether the treaty system can withstand the pressure as those resources become more valuable and more accessible due to ice retreat. History suggests that international agreements hold until the stakes get high enough. Antarctica may be approaching that threshold. The Antarctic Treaty turned 67 years old in 2026. The agreement has survived longer than many predicted, holding together through the Cold War, resource scarcity, and shifting geopolitical alliances. But the treaty contains a clause that makes its future uncertain. In 2048, any signatory nation can request a review conference to renegotiate the treaty's terms. That date sits just over 2 decades away now, close enough that governments are already positioning for what comes next. The treaty system has kept Antarctica peaceful and protected longer than any comparable international wilderness. It banned military activity, prohibited nuclear testing, and preserved the continent for scientific research. Protocol 6 extended those protections by outlawing mining and drilling indefinitely. The treaty represents one of humanity's rare moments of collective restraint, a decision to leave something untouched despite economic and strategic incentives to exploit it. Yet the treaty was easier to maintain when Antarctica seemed worthless. In 1959, extracting resources from the frozen continent appeared technologically impossible and economically absurd. The ice made access too difficult, the climate too hostile, the distances too vast. Nations agreed to preserve Antarctica partly because there seemed little to be gained from doing otherwise. That calculation has changed. Modern technology makes Antarctic resource extraction feasible. Drilling platforms can operate in polar conditions. Icebreakers can maintain year-round access to coastal areas. Satellite surveys have mapped mineral deposits with precision. What was once impossible is now merely expensive. And as global resource scarcity intensifies, expensive starts looking acceptable. Climate change has made Antarctica more accessible as well. Sea ice extent has declined in many regions, opening shipping lanes that were previously blocked for most of the year. Ice shelf collapse has exposed areas of bedrock that had been inaccessible for millennia. Warmer temperatures have made year-round habitation easier, reducing the cost of maintaining mining infrastructure in polar conditions. The continent is becoming less hostile just as its resources become more valuable. This convergence creates pressure on the treaty that its architects never anticipated. Nations that agreed to leave Antarctica untouched when it seemed frozen forever now watch the ice retreat and wonder whether their restraint makes sense. Some governments argue that carefully regulated resource extraction could proceed without violating the treaty's spirit. They suggest that mining operations could be designed to minimize environmental impact, that revenue could fund climate research, that leaving resources untapped while the world faces shortages is wasteful. Environmental scientists largely reject these arguments. They point out that no industrial activity in Antarctica could truly be low impact. The continent's ecosystems are fragile, adapted to pristine conditions over millions of years. Even small-scale mining would require roads, power generation, waste disposal, and human infrastructure that would fundamentally alter the environment. Oil spills in Antarctic waters would persist for decades because cold temperatures slow the breakdown of petroleum compounds. Tailings from mineral extraction would contaminate areas far from mining sites due to wind and ice movement. The treaty review process in 2048 will likely determine whether Antarctica remains protected or becomes the next frontier for resource extraction. If major powers decide the economic value outweighs preservation, the treaty could be renegotiated to allow limited mining. If environmental and scientific communities can maintain political support for protection, the ban might be extended or even strengthened. The outcome depends on global conditions 2 decades from now. If climate change drives severe resource shortages, pressure to exploit Antarctica will intensify. If renewable energy and recycling technologies reduce demand for virgin minerals, protection becomes easier to maintain. If geopolitical tensions escalate, nations may view Antarctic resources as strategic assets too important to leave untouched. The treaty that preserved Antarctica for nearly 70 years is approaching its first real test. What happens in 2048 could determine whether the frozen continent remains a scientific preserve or becomes the last place on Earth where nations compete for the resources beneath the ice. The decision sits just over the horizon, close enough to feel inevitable, far enough that its outcome remains uncertain. Antarctica's fate will be decided not by the ice itself, but by how desperate or wise humanity becomes in the years ahead. Beneath the ice, locked in rock and frozen sediment, wealth beyond measure waits in darkness. The geological surveys paint a picture that would make any mining executive's hands shake. Coal seams thick enough to fuel power plants for centuries. Iron ore deposits that could supply steel mills for generations. Copper, platinum, gold, all in concentrations that would be profitable to extract if only the ice weren't in the way. And rare earth elements, the materials that make modern technology possible, exist in quantities that could reshape global markets. Antarctica's coal deposits rank among the largest on Earth. The Transantarctic Mountains contain seams estimated to exceed 500 billion tons, more coal than currently remains in many producing nations combined. The coal formed millions of years ago when Antarctica was forested and positioned closer to the equator. Plant matter, accumulated in swamps, was buried, compressed, and transformed into the black rock that powered the Industrial Revolution elsewhere. That same transformation happened beneath what is now ice. The coal sits there still, unmined, frozen, waiting. Iron ore deposits in the Prince Charles Mountains could potentially supply global steel production for decades. Geological mapping suggests concentrations comparable to major producing regions in Australia or Brazil. The ore formed from ancient volcanic activity and tectonic processes that concentrated iron-rich minerals into economically viable formations. If those deposits existed anywhere else, mining companies would already be extracting them. In Antarctica, they remain untouched beneath thousands of feet of ice. Rare earth elements present the most strategically important resource. These materials are critical for manufacturing electronics, renewable energy systems, military technology, and countless other applications. Currently, global rare earth production is concentrated in just a few nations, creating supply vulnerabilities that worry governments worldwide. Antarctica's rare earth deposits, if developed, could diversify supply chains and reduce dependence on current producers. Estimates suggest substantial deposits in multiple regions of the continent. Oil and natural gas lie beneath the surrounding ocean floor. The Southern Ocean's geology resembles other productive hydrocarbon basins. Sedimentary layers deposited over millions of years contain organic material that heat and pressure transformed into petroleum. Seismic surveys suggest significant reserves, though exact quantities remain uncertain without exploratory drilling. Some projections estimate the Ross Sea alone could hold 30 billion barrels of oil, roughly equivalent to total reserves in several major producing nations. Natural gas deposits could exceed 500 trillion cubic feet, enough to supply global demand for years. These numbers are estimates, not confirmed reserves. Until companies can actually drill and extract samples, the true extent of Antarctic oil and gas remains speculative. But the geological conditions strongly suggest substantial hydrocarbons exist. The same processes that created oil fields elsewhere operated beneath Antarctica as well. The only difference is the ice that now covers it. That ice is both protection and obstacle. It prevents exploitation while it remains intact, but it's thinning. Some ice shelves have retreated enough to expose bedrock that was covered when the Antarctic Treaty was signed. As warming continues, more land and seafloor will become accessible. The resources that seemed permanently locked away in 1959 might be reachable by mid-century. Mining companies and energy firms pay attention to these changes. Corporate executives don't publicly discuss Antarctic operations because the treaty forbids them. But internal planning documents obtained by journalists suggest that major resource corporations have studied Antarctic geology extensively. Some companies have reportedly developed contingency plans for extraction operations that could begin if the treaty were ever amended to allow development. The economic incentive is straightforward. As easily accessible deposits elsewhere deplete, the cost of extraction rises. At some threshold, Antarctic mining becomes competitive despite the challenges of working in polar conditions. That threshold approaches as technology improves and conventional deposits decline. Environmental costs don't appear in corporate spreadsheets, except as regulatory obstacles. The damage that mining would cause to Antarctic ecosystems, the risk of spills and contamination, the loss of one of Earth's last pristine wilderness areas, these concerns matter to scientists and environmentalists, but rarely to shareholders. If Antarctic development becomes legal and profitable, it will happen. The question is whether humanity values what lies beneath the ice more as resources to exploit or as a frozen archive to preserve. The answer will determine whether Antarctica's geological wealth remains locked away or becomes the final frontier of industrial extraction. The ice holds more than minerals and frozen water. Buried in ancient layers, sealed away for thousands or millions of years, organisms wait in suspended animation. Viruses that infected animals during the last ice age. Bacteria that thrived when Antarctica was warm and forested. Microbes from eras so distant that the species they once infected no longer exist. As the ice melts, these organisms return to the world. Scientists call them zombie pathogens, life forms that should be extinct, but instead were merely sleeping. In 2014, researchers successfully revived a virus from 30,000-year-old Siberian permafrost. The virus, which infects amoebas, returned to full activity after being frozen since the era when Neanderthals still existed. It wasn't alone. Other experiments have revived bacteria from ice cores hundreds of thousands of years old. The organisms emerge from their frozen dormancy and resume metabolic activity as if no time had passed. They prove that ice preserves not just dead matter, but living biology, paused and waiting. Antarctica's ice contains similar passengers. Drill cores pulled from deep ice contain bacteria that DNA analysis suggests have been frozen for millions of years. Some of these microbes come from lineages that modern science has never documented. They represent ancient biology, organisms adapted to environmental conditions that no longer exist on Earth's surface. What happens when they wake up? Most Antarctic microbes likely pose little threat to modern ecosystems. They evolved in isolation and lack adaptations to compete with organisms that have continued evolving over millions of years. Released into today's environment, these ancient bacteria would probably die, outcompeted by species better adapted to current conditions. Probably. The concern arises from uncertainty. Scientists don't know what every ancient microbe is capable of. Some might carry genes for producing toxins or compounds that modern organisms have never encountered. Others might interact with current species in unpredictable ways. The probability of a revived Antarctic organism causing widespread harm is low. But low probability isn't zero probability. And with climate change accelerating ice melt, the number of ancient organisms being released increases every year. Viruses present a different risk profile. Unlike bacteria, viruses require host cells to reproduce. A virus that infected Antarctic animals millions of years ago would need a compatible host to become active again. If the species that virus once infected are extinct, the virus should be harmless. Should be. Viruses sometimes jump between species. A pathogen that evolved to infect ancient seals might find modern seals sufficiently similar to allow infection, or it might not. Predicting viral behavior based on ancient DNA remains an inexact science. Some researchers study these organisms specifically to understand the risks they pose. Labs analyze ice core samples, identifying bacterial and viral DNA, attempting to reconstruct what these organisms were and how they functioned. The work proceeds cautiously because reviving ancient pathogens carries obvious dangers. Protocols exist to prevent accidental release, but as Antarctic ice melts naturally, those protocols become irrelevant. The organisms escape containment without human intervention. Coastal ice shelves that carve into the ocean release meltwater containing whatever microbes the ice preserved. That water mixes into the Southern Ocean, carrying ancient biology into contact with modern ecosystems. Most organisms probably die quickly. Some might persist in niche environments. A few could potentially establish populations if conditions favor them. The Antarctic Peninsula, warming faster than most of the continent, provides the greatest source of melting ice and therefore the greatest release of ancient organisms. The region's glaciers shed millions of tons of ice annually. Each melting iceberg carries microbes that have been frozen since before human civilization existed. Scientists monitor coastal waters for unusual microbial activity, watching for signs that ancient organisms are surviving and spreading. So far, no catastrophic outbreaks have been detected. The monitoring continues because the alternative, missing an emerging pathogen until it becomes widespread, is unacceptable. Biological threats from melting ice aren't limited to pathogens. Some ancient microbes produce chemicals that modern organisms can't metabolize. Released into marine environments, these compounds could act as pollutants, affecting species that have never evolved resistance to them. Other organisms might consume resources in ways that disrupt current food webs. The Antarctic ecosystem exists in careful balance, species adapted to each other over millennia. Introducing ancient organisms into that balance is an uncontrolled experiment with unpredictable outcomes. The melting ice doesn't ask permission before releasing what it contains. Every summer, more ancient layers thaw. More organisms return from frozen dormancy. More biological unknowns enter the environment. Scientists can monitor and study these releases, but they can't prevent them. The ice will melt, and whatever it preserved will wake up. The hope is that evolution has moved on, leaving ancient biology too obsolete to thrive in the modern world. The fear is that somewhere in Antarctica's ice, something survived that shouldn't have. Silence doesn't exist beneath Antarctic ice. The ocean produces a soundscape unlike anything heard elsewhere on Earth, a symphony of creaks, groans, cracks, and reverberations that scientists are only beginning to understand. Underwater microphones called hydrophones, deployed in the Southern Ocean, record this acoustic environment continuously. What they capture sounds alien, a mix of biological activity and geological violence, filtered through water colder and more isolated than any other ocean. The ice itself makes most of the noise. As glaciers flow toward the ocean, they grind against bedrock, creating low-frequency rumbles that travel through the ice and into the water below. These sounds register on hydrophones as deep groans, vibrations that can persist for hours. Scientists can distinguish between different types of glacial movement based on the acoustic signatures. Fast-flowing ice produces sharper, more irregular sounds. Slower, more stable glaciers generate steady, rhythmic vibrations. Ice shelves add their own contribution. As these floating sheets of ice flex with ocean tides, they produce creaking sounds similar to a wooden ship working in heavy seas. The ice bends but doesn't break, creating stress that releases acoustically. When ice shelves do break, when cracks propagate and icebergs carve into the ocean, the sound registers as explosions. Hydrophones hundreds of miles away detect these events, recording crashes loud enough to temporarily drown out all other ocean noise. Researchers use these acoustic signatures to study ice shelf stability. By analyzing the frequency and intensity of creaking sounds, they can estimate how much stress an ice shelf is experiencing. Increases in acoustic activity often precede calving events by days or weeks. The ice announces its own instability through sound. Seals and whales contribute to the soundscape as well. Weddell seals produce vocalizations beneath the ice that range from whistles to trills, calls that carry for miles through the water. These sounds help seals locate breathing holes and communicate with each other in the darkness beneath ice sheets. Whales migrating into Antarctic waters add their own voices, low-frequency calls that overlap with glacial sounds but remain distinct. Trained listeners can differentiate between biological and geological sources, though the overlap sometimes makes interpretation challenging. Then, there are sounds science can't fully explain. Hydrophone recordings occasionally capture acoustic events that don't match known sources. Some produce repeating patterns that suggest biological origin, yet no animal has been identified that makes those particular sounds. Others resemble geological activity but occur in locations where seismic sensors detect no corresponding vibration. These mystery sounds remain catalogued, analysed, debated. One category of unexplained sound occurs in deep water beneath the ice shelves, areas where hydrophones can be deployed, but human observation is impossible. The sounds resemble knocking or tapping, rhythmic patterns that last for minutes before stopping. Some researchers theorize these come from ice fractures propagating in ways that create percussive effects. Others suggest they might be biological, produced by organisms adapted to live in the ice shelf's underside, a habitat we've barely explored. No consensus exists. The recordings continue. In 2015, a hydrophone in the Ross Sea recorded a sound that lasted for nearly 8 hours, a continuous low-frequency tone that slowly rose in pitch before abruptly stopping. Analysis ruled out equipment malfunction. The sound was real, produced by something in the ocean. Yet nothing in the known catalogue of Antarctic acoustic sources matches the event. Theories include iceberg grounding, underwater landslides, or volcanic activity. None fully explain the sound's duration and characteristics. It remains an anomaly, filed away in acoustic databases, occasionally revisited when new listening technology allows reanalysis. The ocean beneath Antarctic ice is louder than people imagine. The popular image of a silent, frozen wasteland doesn't match reality. The ice moves, cracks, grinds, and groans constantly. Organisms vocalize. Water flows through channels carved in ice, creating sounds like rivers amplified through natural resonance. Tides flex ice shelves twice daily, each tidal cycle producing its own acoustic signature. Scientists studying these sounds do more than satisfy curiosity. Acoustic monitoring provides data about processes we can't observe directly. Hydrophones beneath ice shelves tell us when calving is likely, how fast glaciers are flowing, whether ocean currents are changing. Sound reaches places cameras and sensors cannot. It becomes a window into the hidden ocean when all other windows are blocked by miles of ice. The soundscape is changing as well. Recordings from decades past compared to current data show shifts in acoustic patterns. Some areas produce more cracking sounds as ice becomes less stable. Other regions have grown quieter as glaciers thin and reduce their grinding contact with bedrock. The ocean beneath. Antarctica is telling us something through these changes. We're learning to listen. Not every expedition to Antarctica's hidden ocean returns successfully. Some end with equipment lost, researchers trapped, missions abandoned when ice and ocean prove more hostile than anticipated. These failures don't make headlines the way discoveries do, but they shape how science approaches the frozen continent. They teach lessons written in setbacks, frostbite, and millions of dollars of machinery entombed beneath the ice. In 2013, a research team attempting to drill through the ice sheet above Lake Ellsworth encountered problems almost immediately. The drill, designed to punch through more than 2 miles of ice to reach the buried lake below, stopped making progress at less than half that depth. Ice conditions differed from what models predicted. The drill bit overheated despite the surrounding cold, melting ice that refroze around the equipment. Engineers struggled to free the machinery. Days passed while heated water was pumped down the drill hole to try melting the obstruction. The ice won. After 2 weeks of effort, the team abandoned the attempt, pulling equipment back to the surface with the lake still unreached. The mission cost exceeded $10 million. It produced no samples, no data from the lake itself, only harsh lessons about ice drilling in Antarctic conditions. A separate expedition in 2016 aimed to deploy autonomous sensors beneath the Filchner-Ronne ice shelf. The plan involved drilling a smaller hole and lowering instruments through the ice into the ocean cavity below. The drilling succeeded. The instruments went down smoothly. Then ocean currents beneath the ice caught the sensor cables, pulling them away from the drill hole. When the team attempted retrieval, the cables had drifted far enough that they couldn't be reached. Thousands of feet of scientific instruments and cable remained somewhere beneath the ice shelf, lost to currents no one anticipated would be that strong. The sensors probably still function, collecting data that will never be downloaded, transmitting signals that reach no receiver. In 1986, a different kind of disaster struck. Researchers working on the Ross Ice Shelf deployed a submersible designed to explore the ocean beneath the ice. The vehicle descended through a pre-drilled hole, collecting video and samples as planned. On its return journey, ice shifted. The hole the submersible needed to reach the surface was no longer in the same location relative to the surrounding ice. The vehicle's navigation system, designed for open ocean, couldn't adapt to a moving exit point. The submersible ran out of power searching for a hole that had drifted. It sank to the seafloor, carrying irreplaceable data and equipment to a resting place beneath hundreds of feet of water and thousands of feet of ice. Recovery was never attempted. Some researchers have faced more immediate danger. In 2018, a team working on an ice shelf near the Amundsen Sea heard sounds they initially mistook for wind. The groaning grew louder over several hours. By the time they identified it as ice fracturing, retreat options had narrowed. The ice shelf was breaking apart around them, not catastrophically but steadily. They evacuated equipment in stages, prioritizing personnel safety over instruments. The shelf didn't collapse entirely, but sections carved away, taking with them drilling equipment and a temporary research shelter. The scientists made it to safe ice. Their gear did not. These incidents rarely involve fatalities, a testament to safety protocols and the caution with which Antarctic research proceeds, but they demonstrate how hostile the environment remains despite technological advances. The ice doesn't cooperate because humans want it to. Ocean currents beneath ice shelves don't follow predicted patterns. Equipment designed for extreme cold still fails when conditions exceed design specifications. Each failed mission teaches the community something. Drill bits are redesigned. Navigation systems for under-ice vehicles improve. Protocols for monitoring ice stability become more rigorous. Yet Antarctica continues presenting challenges that engineering hasn't solved. The ocean beneath the ice remains partially inaccessible, despite decades of effort and investment. Some lakes stay unexplored because drilling technology can't reliably reach them. Regions beneath the thickest ice shelves have never been sampled directly because no instrument can navigate that environment and return usable data. Scientists accept these limitations while working to overcome them. But acceptance doesn't ease frustration when years of planning and millions in funding produce nothing but expensive lessons about what doesn't work. Antarctica's hidden ocean guards its secrets behind barriers of ice and current that technology can probe but not fully penetrate. The continent has defeated as many expeditions as it has rewarded. Equipment graveyards exist beneath the ice, scattered sites where drills, submersibles, sensors, and cables lie abandoned. Each represents a mission that encountered conditions beyond what preparation could anticipate. They're monuments to human ambition meeting geological indifference, and they're reminders that the frozen ocean beneath Antarctica still sets the rules for who gets to explore it and who gets sent back empty-handed. The future of Antarctic exploration doesn't depend on humans going deeper beneath the ice. It depends on machines that can go where we cannot and return with what we need to know. Autonomous underwater vehicles, submarines that navigate without direct human control, now represent the cutting edge of Antarctic science. These machines slip beneath ice shelves into cavities no person can reach, mapping landscapes we've never seen, collecting data from the most isolated ocean environments on Earth. The vehicles resemble torpedoes more than traditional submarines. Streamlined bodies packed with sensors, cameras, sonar, and batteries. They operate independently for hours or days, following pre-programmed routes or making navigation decisions based on real-time sensor input. Some carry instruments that measure water temperature, salinity, and chemistry. Others focus on mapping, using sonar to build three-dimensional models of ice undersides and seafloors. The best carry both, creating comprehensive surveys of environments humans have only glimpsed. Deploying these vehicles under Antarctic ice shelves requires precision. A support team drills a hole through the ice, lowers the submarine into the water below, and releases it to begin its mission. The vehicle navigates away from the hole, exploring the cavity beneath the ice for as long as its battery allows. Then, it must return to the exact spot where it entered. Find the hole again, and surface within a few feet of the correct location. If it misses, it's trapped beneath the ice until power runs out. Early missions lost vehicles this way, submarines that collected perfect data but couldn't navigate back to their exit point. Engineers learned. Modern vehicles carry multiple navigation systems, redundancy designed to prevent the losses that plagued earlier generations. GPS doesn't work under ice, so the submarines rely on inertial navigation, acoustic beacons, and terrain matching algorithms. They memorize the route outbound and reverse it on return. Success rates have improved dramatically, though occasional failures still occur when ice conditions or currents create situations the vehicles can't handle. What these machines have discovered justifies the investment. Submarines deployed beneath the Pine Island Glacier ice shelf in 2022 returned with video showing deep channels carved into the ice underside. Grooves, dozens of feet deep, where warm water flows like rivers through ice. The channels funnel ocean heat directly to the glacier's grounding line, the point where ice transitions from resting on bedrock to floating on water. This is the glacier's most vulnerable location, and warm water is hitting it with precision. The same mission mapped the seafloor beneath the ice shelf, revealing underwater ridges that once stabilized the glacier but no longer do. The glacier has retreated past those ridges, removing a barrier that previously slowed its flow into the ocean. The vehicle's data showed exactly how and when this retreat happened, filling gaps in scientific understanding that satellite observations couldn't address. Other submarines have explored beneath the Ross ice shelf, mapping an area larger than France without a single human entering the water. The vehicles revealed seafloor features that models hadn't predicted, including valleys that channel warm water toward the ice in ways that could accelerate melting. They documented biological communities living in near-freezing water, organisms clustered around features that provide nutrients or shelter in an otherwise barren landscape. Autonomous technology allows missions that would be suicidal for human divers. Water temperatures beneath Antarctic ice hover just above freezing. Currents can exceed several knots. Visibility varies from excellent to zero, depending on sediment and biological activity. Disorientation under the ice, where every direction looks identical, would be lethal. Machines don't experience cold, don't get disoriented, don't panic when their surroundings become unfamiliar. They execute their programming and return, or they fail and sink. Either way, no lives are risked. The vehicles keep improving. Newer models can operate for weeks rather than hours, covering hundreds of miles before requiring a retrieval. Some communicate with operators through ice, using acoustic signals that penetrate where radio cannot. This allows real-time mission adjustment, the ability to redirect a submarine when it encounters something unexpected. Future vehicles will carry more sophisticated sensors, including instruments that can detect DNA in seawater, identifying organisms without needing to capture them. Others will sample sediment and drill into bedrock, collecting cores that reveal geological history. The goal is comprehensive understanding of environments we cannot physically access. Antarctica's hidden ocean is being mapped by machines we send into darkness and hope return. They represent our eyes and hands in places where biology fails. Each successful mission brings back pieces of the puzzle, data that helps predict how fast ice will melt, where ocean currents flow, what lives beneath the ice. The submarines are rewriting our understanding one mission at a time, diving into an ocean humans will probably never explore in person. The ice is too thick. The water is too cold. The distances are too vast. So we build machines that don't need warmth or air, or the comfort of knowing they can surface whenever they want. And we send them beneath Antarctica to see what comes back. The ice will not last forever. Every glacier that flows toward the ocean, every ice shelf that thins and fractures, every summer that melts more snow than winter replaces, brings Antarctica closer to a version of itself unrecognizable from what exists today. Scientists debate timelines and magnitudes, but the direction isn't in question. The ice is leaving. What it reveals will reshape our understanding of the planet. First will come land. Bedrock currently buried beneath miles of ice will see sunlight for the first time in millions of years. The rock will be scoured smooth by glacial movement, scraped clean of soil and loose material. Lakes will form in depressions where ice once sat, filled by meltwater that has nowhere else to drain. These lakes will be sterile at first, devoid of life because nothing has survived the grinding passage of glaciers above. But organisms will arrive, carried by wind, birds, ocean currents. Within years, these new lakes will host microbial communities. Within decades, more complex ecosystems may establish themselves. The coastline will change dramatically. Ice shelves that currently extend hundreds of miles into the ocean will disintegrate, exposing bays and inlets that no map has recorded. Islands will emerge, pieces of land that are currently beneath ice but sit above sea level on bedrock. Antarctica's area will appear to shrink as floating ice vanishes, even though the continent's actual landmass remains unchanged. Geographers will redraw maps repeatedly as the ice front retreats. New mineral deposits will become accessible. Resources currently locked beneath glaciers will lie exposed on the surface, ready for exploitation if legal frameworks allow it. The race to claim these resources could intensify conflicts over Antarctic territory, testing whether international agreements hold when economic incentives become overwhelming. Marine ecosystems will expand into areas currently covered by ice. Species adapted to open ocean will colonize regions that have been ice-covered for millennia. Competition between native Antarctic organisms and invaders from warmer waters will reshape food webs. Some species will thrive in the new conditions. Others will decline as their ice-dependent habitats vanish. Penguin colonies that rely on sea ice for breeding may collapse. Fish species adapted to live beneath ice shelves will lose their habitat. Seals that haul out on ice floes will need to find alternative resting sites. The ecological disruption will cascade through the Southern Ocean, affecting species far from Antarctica as currents and nutrient distributions change. Sea level will rise, not gradually but in surges as major ice sheets collapse. Coastal cities will flood. Small island nations will vanish beneath the waves. Hundreds of millions of people living near coastlines will be displaced. The economic cost will exceed anything in human history. Insurance systems will collapse. Real estate markets in vulnerable areas will crash. Governments will spend trillions on adaptation measures that buy time but can't fully prevent the ocean's advance. Agricultural patterns will shift as changing ocean currents alter rainfall distribution. Fisheries will collapse in some regions as temperature and nutrient changes make waters uninhabitable for commercially important species. New fisheries may emerge in areas that were previously too cold, creating winners and losers in global food systems. Fresh water from melting ice will alter ocean salinity, potentially disrupting currents that regulate global climate. If Antarctic bottom water formation shuts down, the consequences will ripple through every ocean. Temperature gradients will shift. Weather patterns that have remained stable for thousands of years will change. The tropics could become hotter. Mid-latitudes might experience more extreme seasons. Climate models struggle to predict the details because the system has too many interconnected variables. Yet, beneath the uncertainty, one fact stands clear. The world with less Antarctic ice will be dramatically different from the one we know. Antarctica won't become tropical again, at least not within any time frame relevant to human civilization. Even with aggressive warming, the continent will remain cold. But it will transition from a frozen desert to a partially ice-covered landscape, somewhere between its current state and the forested continent that existed millions of years ago. Scientists will study the transformation as it happens, documenting every stage. Knowledge gained will be immense, a real-time case study in how planetary systems respond to rapid change. But knowledge doesn't prevent the changes, only helps us understand them as they unfold. The ice will retreat. The ocean beneath will become the ocean above, merging with the Southern Ocean in ways that erase the boundary between Antarctica's hidden waters and the rest of the world. What was isolated will be exposed. What was frozen will flow. And we will discover exactly what we've been melting, whether we're ready for that knowledge or not. The frozen ocean beneath Antarctica keeps scientists awake at night, for reasons most people never consider. It's not just the ice melting or the sea level rising. It's the realization that we built civilization on a planet whose most powerful systems we barely understand. Beneath miles of ice, in darkness and cold beyond human experience, processes unfold that control climate, ocean circulation, and the stability of ice sheets holding enough water to redraw every coastline on Earth. We've sent machines into that darkness. We've drilled through the ice and pulled up samples. We've mapped portions of the hidden ocean and documented what lives there. And every answer we find generates more questions. Every mystery we solve reveals deeper mysteries beneath. The ocean under Antarctica doesn't operate by rules we learned from studying tropical seas or temperate coastlines. It's colder than water should be able to remain liquid. It harbors life in forms that challenge our definitions. It connects to volcanic systems we didn't know existed, and drives currents that affect weather patterns thousands of miles away. It's waking up. That's what terrifies researchers who've spent careers studying the frozen continent. The ocean beneath the ice isn't stable. It's changing faster than models predicted, warming from below and above, melting ice that has persisted for millions of years. The changes are accelerating. Ice shelves that should take centuries to collapse are disintegrating in decades. Glaciers that models suggested would retreat slowly are sliding into the ocean faster each year. The feedback loops are engaging, systems where melting creates conditions that cause more melting, cycles that become self-reinforcing until something breaks. Scientists point at graphs showing exponential curves, ice loss rates that bend upward sharply. They explain tipping points, thresholds beyond which change becomes irreversible regardless of what actions humanity takes. Some of those thresholds may have already been crossed. We won't know for certain until the consequences become obvious, by which point prevention is impossible. The ocean beneath Antarctica holds Earth's last unknown world, a frontier that remains partially unmapped, despite satellites and submarines, and decades of research. It's alien enough that studying it prepares us for exploring ice-covered moons around other planets. Yet it sits at the bottom of our own world, influencing every system we depend on, responding to changes we've caused through emissions and development, and the cumulative impact of 8 billion people altering atmospheric chemistry. The ice above it is melting, the water beneath it is warming. The timeline for how long Antarctica's frozen ocean remains hidden is shrinking. What we find as that ocean emerges will determine whether coastal cities survive or flood, whether ocean currents continue their current patterns or shift into configurations that change global climate, whether the biological communities adapted to life beneath the ice can transition to open ocean or go extinct. The answers exist now, written in ice layers and ocean temperatures, and the behavior of glaciers we're only beginning to understand. Scientists race to read those answers before the evidence melts away, documenting a world that's disappearing even as they study it. Antarctica's hidden ocean terrifies researchers because it represents power beyond human control. Systems so vast and interconnected that our ability to influence them came as a surprise. We didn't mean to destabilize Antarctic ice. We didn't intend to warm the ocean beneath it or accelerate the melting that releases ancient ice into the sea. Yet intentions don't matter to physics. The ice melts whether we meant for it to or not. The ocean warms. The consequences unfold. And beneath the ice, in the last unknown world left on Earth, changes are happening that will define the future for every person alive today and every generation that follows. The frozen ocean beneath Antarctica isn't just a scientific curiosity or an extreme environment worth studying. It's the sleeping giant we accidentally woke up. And now we watch, measure, and model its awakening while hoping we can adapt to whatever comes next. The ice keeps its secrets for now, but the ocean beneath is rising, warming, preparing to emerge. What it reveals will be Earth's last surprise, the final frontier not in space but beneath the frozen surface of the least known continent. The terror comes from knowing we're about to find out what we've been standing on all along.